In this module, we're looking at the different storage options that we have for storing our databases. We're going to talk about the different storage concepts and some of the storage components that are available to the SQL environment. We're going to look at the effect that these storage environments and storage I/O has on the performance of the SQL Server. Then we're going to start to look at some of the alternative options we may have for storing our databases. We're going to look at SMB File Shares, SMB version 3 file shares. We're going to look at using Azure as a destination storage location for database files. And then we're going to talk about Stretch Database, where we can optimize on-premise storage by migrating and moving infrequently used data out to Azure. So when we start to look at configuring the SQL environment, one of the most important factors is going to be the I/O performance. And when we talk about I/O, for us mostly when we talk about SQL Server, we're talking mostly about disk I/O. So it's critical to the performance, but it's important to understand that different types of databases are going to have different I/O performance requirements and characteristics. So read-heavy operations are going to have different characteristics than write-heavy operations. Now your text goes into a discussion again of something we've already talked about, which is the process that changes are made in a database. And remember, it goes through the transaction log, but before any changes can be made, everything's got to be pulled from disk, pulled into memory, the changes are made in memory, and then they're committed and written from memory into the database and marked in the transaction log as complete. Until that write to the transaction log occurs, the transaction is not considered finalized and complete. So you have to design your storage solutions around the types of databases that you have, as well as the types of workloads that those databases are going to be using. Now, there's different ways to identify workloads. If you have an existing database, you can use tools like SQL Profiler, and we can even query some of the dynamic management views like the I/O virtual file stats to identify which virtual files are being created and how they're being accessed. But if you don't already have a database, it's kind of hard to predict this. But don't forget, when we talked earlier about upgrading in SQL, you can run SQL I/O Sim to simulate disk I/O activity to identify some of the characteristics you're going to experience when you do implement your database. So when a SQL process is attempting to access the input-output operation environment, if it can't do it immediately, it's going to end up in what we refer to as a wait state or a wait environment. So there are different ways to identify the statistics of when wait operations are occurring and when things are waiting for functions to happen. There's a bunch of dynamic management views that we can query. We can look at OS waiting tasks, things that are the SQL Server OS is waiting to access the environment. We can look at wait stats, just overall statistics for different processes that are waiting for time. And we can also look for session wait stats, which is specific query sessions that are being paused to access I/O environments. The different types of waits that can occur based on the input-output operations, latch waits are essentially waiting for data to be read into the buffer cache. Write log waits are waiting for data to be flushed out of the memory into the transaction log. The log buffer waits are waiting for a buffer to be allocated to write the log data into the transaction log. Then you have async I/O completion and I/O completion. Async are things that are not related to a SQL synchronous activity. So things like backup operations could cause wait states to occur, but that's not directly related to an internal process. I/O completion waits is waiting for things like reading from a transaction log for a rollback indication or a commit indication, and so it has to wait for that synchronous process to complete. So when we look at evaluating hard disk drives, an older methodology of identifying hard disk characteristics was to look at things like spindles. And a spindle for today's environment just simply means the existence of a physical disk. In older days where we had rotational or spinning hard drives, there was one little post that ran up the middle and all the platters were attached to that post or that spindle. The rate at which the drive spins usually means faster access time to the data that's on the different platters. The number of platters could affect the read write operations, because you could have multiple heads reading data from multiple surfaces inside the spinning disk. The seek time, the amount of time it takes the head to get from a central location, usually sector 0, out to where the data actually is, was a way of identifying and comparing hard drives. And remember that hard drives are going to have to read data from different blocks on the disk as the disk spins, which causes the head and the arm to have to move in and out to access the data. We can overcome this a lot of different ways. Your book is going to tell you one of the ways is to add more physical disks, add more spindles, so that I can access data across multiple disks simultaneously. We can also simply eliminate the spindle concept and go to solid state drives where the data is electronically stored without any moving parts. That will improve the efficiency. The one thing you have to keep in mind when we talk about solid state drives is they're fairly new to the marketplace. I mean, spinning hard drives have been around for over 40 years. The SSDs have not been around very long, and we really don't know the usable lifespan of these things yet. However, for a lot of organizations, they're starting to go to this because the improvement in performance greatly outweighs what we can plan on the lifespan. You just have to make sure you have some type of recovery process in place to try to improve and make sure you can recover in the event that these drives have a shorter lifespan than we initially expect. So we talked about RAID earlier, redundant array of inexpensive or independent disks. RAID 0, striping without parity. Again, no fault tolerance here. RAID 1, mirroring or duplexing if you use 2 controllers. RAID 5, striping with parity. RAID 10, mirrored stripe sets. When we look at this process, remember that mirroring cost me 50% of my storage. Striping with parity costs me 1 over the number of drives in the set in my storage. Striping without parity gives me great performance improvements, but 0 fault tolerance, so we want to avoid that unless we have some other fault tolerance mechanism in place. The best of all of these is the combination of the striping without parity that's being mirrored, so that's RAID 10. But again, that costs us 50% of our storage. So storage spaces is a feature of Windows Server, and what it allows us to do is combine disks from multiple different environments and bring them into a pool and then allocate the pool to different environments to use the data in the pool. Within the pool, we can also create tiers that allow us to identify certain types of disks that have a better performance, and we can use those for specific functions. So with storage spaces, we can pull the disks together. These disks can be both internal and external disks. We can add internal IDEs, SATA, external USB drives, SAS drives. We have multiple resiliency options when we create the pools. We have mirrors, we have 2-way mirrors, we have 3-way mirrors. We have parity sets that we can define that allows us to create fault tolerance and the ability to recover in the event that there's a failure of one of the disks. The big advantage of storage pools also is that if for some reason we start to run short on space, we can simply add another drive to the physical system, either attach it to the outside or put it on the inside storage array, and simply add that disk to the storage pool without having to modify anything. And all of the new space that's been allocated to the pool automatically becomes available to the systems that are accessing the pool. So it allows us to create fluid storage environments without having to modify the physical infrastructure of the environment, and without having to do things like in the old days in Windows, if you wanted to add space to a system, you had to create a mount point and extend the drive across the mount point or create a spanned disk. Here we don't have to worry about that. We simply add space to the pool and it's available to the disks that have been defined on the pool. So the process for implementing storage pools is you go into the Windows Server Manager, and in Server Manager you go to the File and Storage Services, you click on the tasks and you say create a new pool. When you create a pool, you give it a name. You also specify the disks that you want to be added to the pool. Once you create the pool, you then create a storage space in the pool. With the storage space, you identify the disk that you want to create. You create a virtual disk. You determine the tiers that you want. And this is where you determine the type of resiliency that you would like to use for the storage space. After you create the virtual disk, the disk appears to the different components that connect to the environment. And from that disk, you create volumes. Just like you would if you attached a physical disk to a system, you would click on the disk, and then from that disk, you would create a volume. So this allows us to then identify the disk that's been attached to the system, in this case, the virtual disk. And from that, I can then create one or more volumes inside of that virtual disk. So when we look at how indexes affect performance, think about a table that we have that has no index on it. And we're looking specifically for some records that have a particular order ID, let's say. So we go into the table and we want to find all of the rows that have that order ID. Well, without an index, what we actually have to do is we have to go through every single page in that table, and we have to look for every single row to see which rows are going to have that particular order ID. And that's referred to as a table scan. And so what that table scan is going to require is, as the name implies, we have to scan all of the data pages that are being used to hold that table. When we have an index on a table, if this is an example of a clustered index, what we have is we have a root page, and that root page is going to have all of the information specifically about the rows of pages that have the data on them, and it's going to tell us the ranges. I mentioned this earlier. Think about this like if you walked into a library. So we have essentially, for those of you that are old school, a card catalog. And the card catalog is going to have a list of all of the books and what their ID is. And then it's going to tell us a general area where we can get to those books. Then we go to the row of the books, the shelving systems, and that's going to be an intermediate page. So that intermediate page here is going to have all of the information about the different books, and it's going to have a range. And that range is then going to point us to a particular area of the bookshelf and a specific shelf. And on that shelf, that's the equivalent here of a page. And that shelf right here is going to show us the page information. And then we know that on that page is the record that has that specific ID. That is how we use indexes. Now, before you go too crazy and just say, well, why don't we just create indexes on everything? The problem is we have to store all this information. So all this information down here is going to have to be stored in the database as an object. It also requires maintenance. We have to maintain this. Every time we add a new row to the environment, we're going to have to modify these pages, maybe, these pages most likely, and these pages down here, definitely, to insert the new row, to put it in the correct position where it belongs, so that when we go to look for it later on, we can find what we're looking for. But in most cases where we have clustered indexes and we have primary keys, it makes retrieving data and finding that data much more efficient. In real life, when you're going to do this, you're going to want indexes on any columns that you're going to do joins on, or that you're going to use as the primary key column for a specific table. So remember, the Tempdb database is a system database that, unlike the other system databases, doesn't permanently maintain any objects. So every time the SQL Server service starts, the Tempdb is cleared, and anything that was in there previously is gone. It's used for building result sets, sorting data, filtering data. It's used for creating user objects when we're using things like stored procedures and views. It's used for versioning of rows when we're using row versioning functions. It's going to use a different amount of space depending on what's going on currently on the system. And we talked about it previously. In the older versions of SQL, we could have put this in memory, Tempdb and RAM, but that didn't work out so well. So now what they're recommending we do is we actually create multiple files for the Tempdb, and you already saw in a demo that we created multiple files for Tempdb, and then we spread those out across multiple disks. If you have only one or two solid-state drives available to you for this, for SQL Server, then the Tempdb is probably one of the best places to put that. to put on those SSDs, because you're going to get the best performance across the entire SQL Server as opposed to a single database or a single table or component within a database. So we can split the Tempdb up into multiple files. They should all be of equal size. And if you remember earlier, they recommend one Tempdb file for every core in the server. As you add more and more cores, you can reduce that ratio. But up to about 8 cores, they recommend one file for each core for the Tempdb database on a separate subsystem. You don't want to be competing with space with the operating system or with the SQL Server data files with the Tempdb, because you're going to want to be able to put stuff in the Tempdb at the same time be able to read stuff from the database files and from the buffer cache from the database files to bring into the buffer cache so you can operate on those objects. In this demonstration, we're going to look at how to move the files for the Tempdb database. In this demonstration, we're going to look at how to move database files. Now, you might remember in a previous demonstration, we moved the Tempdb files. In that demonstration, we only moved the primary database file and we moved the log file. In this example, we're going to move all of the database files for the Tempdb. Now, just like before, we want to go into the system databases and we want to go into Tempdb, and in the properties, we're going to look at the files and the file locations. So if we click on the files, just like we saw earlier, you can see they're all stored in the C:"program files directory. So now what we're going to do is we're going to look at how to move these and move all of them, right? So we have the tempdev, we have the temp log, and then we also have 2, 3, 4, 5, and 6 for temp files. So we'll cancel out of this, and here's the script file that we're going to use. So we'll alter database, the name of the database, modify the file, the logical name of the file, and the destination. Now, notice these are all going to go in the root of the D drive. So if we go to the root of the D drive, you will see that there are no files. So let's go ahead and run this command, and this is going to move all of the database files. And that moves all of my database files. And now we're going to move the log files. The log file, there's only one of them. So notice it tells you it's been moved, modified in the system catalog, but the new path won't be used until the next time the SQL Server is restarted. So again, just like we saw in the previous demonstration, there's nothing in the D drive because nothing has been moved to that location yet. So we go to the SQL Server, we say restart, same warning that we had before. Remember that restarting the SQL Server is going to kick everybody off of it. Any transactions that are currently in process may be lost. Transactions may be rolled back, so be cautious about doing this during regular activity periods. Try to do this during low activity periods when possible. And so this is going to stop the SQL Server, read the master database, which is going to define where the Tempdb files are stored, and it will then move them all to the Tempdb, the new location. So now if we go to the D drive and we open up our D drive, there's all the Tempdb files. So that's how we move database files. The process is the same regardless of what database we're talking about. The other databases won't require you to restart the SQL Server. They will simply require you to stop and restart the database. Take the database offline, bring it back online. Sometimes it'll just move it automatically. It depends on whether there's any activity in the database or not. In this demonstration, we got to see the process for how to move files with the Tempdb database. We also got to see how you might add additional files for the Tempdb database. So other than internal drives on the physical server that SQL is running on, some other options for storage: network attached storage, generally not recommended for SQL because usually network attached storage does not have the speed with which SQL Server needs to operate. Now, you have to understand that when we talk about things like iSCSI is not a network attached storage environment. It's more considered a SAN configuration, so storage area network. Network attached storage would be more like something that operated like a file server that had file shares that would be providing access through an operating system. Direct attached storage, you have an enclosure and you have drives that are installed inside the enclosure. They appear as though they're internal to the system even though they're in a separate enclosure. And storage area networks, fiber channel storage area networks, and iSCSI storage area networks are very common uses for database I/O and storage operations. Just keep in mind that when you start to use network-based connections, you have to make sure that there's some type of redundancy in the network connection in case the path to the storage array becomes unavailable. You don't want the database to be unavailable. In terms of iSCSI, for example, they say implement something called multipath I/O, MPIO, so that you have multiple paths across the network to that storage infrastructure. So SMB is Microsoft's file sharing protocol. It refers to server message blocks, and it's been around for a long, long time, way back to the old LAN manager days. It was originally used for just file and printer sharing. SMB protocols can also be used for some other things. They've made some great improvements in this protocol starting in Windows Server 2012. So the version of SMB actually changes from version 2 to version 3 starting in Server 2012. That's when the improvement starts. And some of the things that we get now with SMB file shares is the ability to configure fail-out clusters. So we can actually specify scale-out file servers that use SMB for storage. We can set up failover clusters for the file servers. So we can now start to use file shares as methods to store SQL databases without giving up performance issues that we would normally have gotten with older network attached storage environments, and still having the fault tolerance and the failover functionality that we come to expect with things like SANs without the high expense of the SAN infrastructures and the SAN components. When we connect to these file shares, we use the normal, some people call it whack, so // server name / share name. And in a demonstration, you're going to see how to use a file share, but it's really not that much more difficult. When you create a database, when you specify the file name property, you just put in // the server name / the share name / the file name that's going to be on that share. Now to do this, we're going to look at it in a second. There's certain permissions that the SQL server has to have in order to be able to access these shares, and we're going to look at that in the next slide. So when we look at the benefits of SMB file shares in comparison to things like storage area networks, the big benefit is cost. There's no big cost associated with this. We already have file servers that are out there that are running Server 2012 or later. We can implement the SMB version 3 protocol, and we can implement these file shares to access those environments. We also get the ability to manage them with the tools that are normal to the Windows environment. So we use the Server Manager utility, and we use the components within the Server Manager utility to manage these file shares without having to learn any new tools like we would have to if we were doing some type of SAN storage or some type of iSCSI storage that was proprietary. So as mentioned previously, we want to implement SMB file shares for SQL Server to store its databases on. The first thing we have to do is make sure that the SQL Server service account that the SQL Server service is running under has full control to the share. Now, if you remember way back when we looked at how you set up the services, this is one of the reasons why we would use a domain user account so that we can assign this permission across a file share that's on a different server. The SQL Server agent service account also needs full control to access the share, mainly because for things like jobs, in order to be able to read from the databases and access the data within there, it all depends on what components and features you've implemented as to whether the agent actually needs this permission or not. You use the UNC path as mentioned previously when you create the database. So you would say file name equals, and you'd specify / the server name, / the share name, / the file name. That would tell it you're going to retrieve the information and you're going to store the information on a file share. Now there are some limitations here that you need to be aware of. One is you can't use the built-in administrative shares. So that's $, admin $, IPC $. Those cannot be used for the path. You have to create a share. Now, it's important to note, you could create a hidden share, it just can't be an administrative share. You can't use loopback shares. In other words, you can't use / 127.0.0.1, which would loop it back into itself. You also can't create map drives. If you had a map drive, you would have a drive letter, not the share. So you can't specify a map drive in the SMB file share. You also cannot do file stream storage on SMB shares. File stream storage actually goes into a folder location, not a share location. So we can't use SMB shares for file stream storage. In this demonstration, we're going to look at how to create a database and store the database files on an SMB file share. In this demonstration, we're going to look at how to create a database on an SMB share. Now, we've already talked about the benefits of the SMB shares and some of the features and functions and benefits that you get. So now we're going to look at how to use those shares to store a database. The first thing we want to do is we want to go to the SMB share that's already been created for the lab, and we want to look at the properties of this share. So when we go to the properties, you'll get to see the sharing tab, and you'll see that it's already shared as SMB share. And the permissions have already been set so that the SQL Server agent and the SQL Server service have full control to the share. So now what we're going to do is we're actually going to run a script that's going to create, before we do that, let's go ahead and look, and you'll see that there are no files in it. So now what we're going to do is we're going to create a database on that share. So here's the example. It's exactly the same as creating any other database, just when you specify the file name, you don't use an absolute path. Instead, you use a file share path. So the name of the server that the share is on. This could also be a clustered shared file service, okay? The name of the share, and then the name of the data file, and the name of the log file. So we will go ahead and execute this. Again, remember when you're creating databases, you're in the master database. And so now if we go back over to the SMB share folder, you're going to see that there are two files there. And so now these files are on a share. We get the benefits of the share. We get the benefit of easily moving databases, attaching and detaching without having to copy and move files around. In this demonstration, we got to see how to create a database and store the database files on an SMB file share, and how to use the location information with the file server name, share name, and file name where we're going to store the database. Now, one of the new technologies that we can leverage when we're creating SQL Server storage environments is Azure Storage. And what it lets us do is it lets us create a storage location for data from a SQL database out in Azure, or the cloud as most people are going to call it. And what we do is we actually have these things called page blobs that are going to be used to store the SQL data out in Azure. Now, virtual machines have always been able to store their data, Azure virtual machines, in Azure Storage. And what this lets us do is put the different information out there. This could allow us to migrate easily. It could create a fault-tolerant environment where we can do site resiliency so that the data files are at a network internet location, so we can always access them even if a single data center has a problem. When we do this, there's some steps you have to do in Azure first. Now, obviously, you have to have an Azure subscription. And then within that Azure subscription, you're going to have to create a storage account. And then after you create the storage account, you're going to have to create a blob store. And then within the blob store, you're going to then create your page blobs. A single page blob has a limit of 1 terabyte, and you can only have a maximum of 5 page blobs in a storage container. Now, you can create multiple storage containers to overcome that limitation, but that's important to understand. It's also important to note that if you lose the ability to connect to the internet, you lose the ability to connect to Azure. So you have to think about this, and we're going to look at some of the options here for how we can set this up. There's ways to create connections directly to Azure that don't have to go through the general internet. And there's also ways to set up secure connections from your on-premise environment to the Azure environment there, and that would be a VPN. And we're going to look at how to do that in the next few slides. So some of the benefits that we get by storing our SQL Server data files in Azure include easier migration. So this could be one way of migrating your data. You can store the data files in Azure and then spin up a new SQL Server instance in a different physical location and simply attach the file, so attach the database, to the new instance and reference the Azure data files. It's a separation of the compute and the storage environments from each other. So the compute environment is the SQL Server environment, and the storage is now running in Azure. Probably one of the bigger benefits that we get is the database recovery concept. Now, two things are in play here. One is that SQL Server can then be recovered more easily by simply reattaching this data to a new SQL Server instance for migration, but also for recovery. So if I have a SQL Server that dies, physically dies, the box dies, I can simply spin up a new SQL instance and connect to that data, and boom, the database is back online very, very quickly. In addition, Microsoft backs up their data across multiple data centers. And we're going to look later on at how we can control the redundancy of this data. We can do geo-redundancy, where it automatically copies it across multiple data centers. That means we don't have to worry about that concept of providing fault tolerance for those data files like we would if we had them stored on premise. We have security. When you store SQL data files, the data is stored using SQL Server's transparent data encryption, or TDE encryption. That TDE encryption is going to encrypt the data where it's stored, but the key itself is actually stored in the on-premise SQL Server. So anybody that accesses that data out in the cloud cannot access or read or decrypt that data because they don't have the appropriate key to do that. In addition, when we look at this process, the connection between the SQL environment and the data files is protected by TLS encryption. So transport layer security is going to provide protection in the data as it's being transmitted back and forth. It could also be used for, again, for a backup strategy, because the data is already stored somewhere else. We could then use the Azure backup components and copy those data files across multiple containers in Azure, or we can simply rely on the redundancy features that Azure has built into it, and we can turn on geo-redundancy and some other options to provide protection for those data files. So this is a quick introduction to the types of storage objects that are available in Azure as of this recording. There's two different types of storage accounts that you can create. So remember, the first thing we have to do is create a storage account. The storage account allows me to define what types of data is going to be stored there. So in a general purpose storage account, you have blob stores, you have queue stores, you have file share stores, you have virtual machine stores. With SQL, it has to use a blob store. It has to use a page blob, technically. So we have to use general purpose accounts. We create the general purpose storage account, and then within the general purpose account, we create a page blob. We create a blob storage container, and then we create the page blobs within that storage container. In addition, there are two types of storage tiers. There's a standard tier and there's a premium tier. The premium tier is obviously more expensive. Premium tiers currently only support virtual hard disks for virtual machines, so we can't use that for the SQL storage, the SQL data stores. So when you want to use Azure for SQL data stores, you must create a general purpose storage account and then create a standard tier for that storage account. So in order to use Azure to store your SQL Server data files, you create an Azure storage account. Remember, it has to be a general purpose storage account, standard tier. Then you create a blob container within that tier. After you create the container, you're going to have to generate a shared access storage key. And what that shared access storage key is going to do is it's going to identify a key and a name that you're going to use to access that environment. That key becomes essentially the authentication token that's going to be used to decrypt the data inside the storage container. Then on SQL Server, you're going to create a credential that points to the storage container URL and identifies the key that's going to be used to access that. That's going to be the secret. After you create the credential, you then create the database, and when you say file name equals, you put in the URL for the container that you identified when you created the credential, and you also then identify the actual file name that you're going to use. It's going to use the credential information that's already been defined in order to be able to access that data and use the key to decrypt and encrypt the data that's stored at that location. So one of the new features of SQL Server 2016 database engine is this concept of stretch database. And what a stretch database lets us do is identify a cloud storage environment that we can archive data, for lack of a better way of looking at it. We can move data that's not frequently used into the cloud environment and then leave the current data, the data that's used on a regular basis, in the on-premise environment. What that does for us is we can back up just the on-premise data, because Azure is automatically going to make sure that the data stored in Azure is going to be backed up, or we can put it in geo-redundant storage. It reduces the storage requirements of the on-premise environment. We don't have to have as much storage space, and then we might be able to afford faster local storage devices because they don't need to be as large. And it's completely seamless to the users. The users have no direct indication of what data is stored in the on-premise part of the database and what data is stored in the stretch part of the database. There is a little note in your text, however, that does mention there might be a slight delay if users are attempting to access the data that's stored in the stretched part of the database. So because it's got to make that connection through the internet out to the cloud storage environment and retrieve that data to the on-premise query to return the results. So there might be a slight delay, but there's no indication to them that that data is coming from either the cloud or from the on-premise environment. So the way the stretch database works is once we enable a database for stretch, it creates a remote endpoint in the Azure environment. So we get an Azure remote endpoint for the SQL environment. And then once we enable the migration for a table, data from that table is then going to be copied or migrated out to the Azure environment. When users run their queries are always submitted against the on-premise version of SQL, and then that query is sent to both data sources to identify any data that meets the conditions of the query. The data is then returned from the remote endpoint in Azure, if there is any, and then that whole data set then is put together as a single data set returned to the user. And as mentioned previously, the user really has no way of knowing that that data is coming from the stretch part of the database. It is important to note that users cannot query the Azure remote endpoint directly. They have no permissions to that. All the permissions to the data are being configured and controlled from the on-premises copy of the database. So to set up stretch database, there are certain permissions that have to be enabled. In order to enable stretch database on any database, the SQL Server instance has to be enabled for stretch database first. And to do that, you have to be a member of the sysadmin role or the server admin role on SQL Server. So you configure the SQL Server settings for the instance that enables the stretch database. Then once you do that, you have to turn on stretch database on a per database basis. In order to do that, you must be an admin of the database or have the control database permission, and you must have the administrator permissions for the remote endpoint in Azure. It's got to be able to create the connection to the Azure remote endpoint. Once this is set up, all of the permissions for accessing the data are configured on the local on-premise database, and then what data is going to be transmitted to the remote endpoint is defined based on the table. So once we enable the stretch database property for a database, we then turn on the migration feature on a table-by-table basis within that database. Anybody that has configure rights for a table can configure that table to be stretch once an administrator for the database with the control database permission has set up the database for stretch and configured the endpoint. So before we attempt to stretch a database between on-premise and the cloud, the first thing we want to know is, are there going to be any issues that may cause problems with this database after we stretch it or prevent it from being stretched. And to do that, we run the Data Migration Assistant, which we've talked about previously. It will actually analyze and evaluate potential stretch problems with the database. It will look at compatibility issues. It will also then highlight any issues that it knows are there, and it will also identify any things that might block the database from being stretched to the cloud environment. So after we've evaluated a database through the Data Migration Assistant, we know that we can stretch this database out to the cloud. We can do the entire process using the SQL Server Management Studio. So we don't have to do anything in Azure ahead of time other than set up an Azure SQL database. All right, so that has to be done. But once we have that set up, we can actually then run the Stretch Database Wizard from the SQL Management Studio, and that will walk us through the process of connecting to the Azure environment and storing part of our database out in our Azure SQL database. You could, if you wanted to, also run transact SQL statements to implement this so that you can save the script, rerun the script in the future if you needed to, or modify the script to stretch another database. If you had a bunch of databases that you wanted to stretch, you could simply modify the script a little bit. But it can be done entirely in the Management Studio through a wizard. In this lab, you're going to look at how to implement Stretch Database. You're first going to download the Data Migration Assistant and then implement the Stretch Database Wizard to identify the database that can be stretched. Then you're going to actually implement the Stretch Database. This lab's going to take about 45 minutes.